Last week, but I just wanted to refresh our memories. We have actin monomers, so those are those globular proteins. They're not perfect spheres, but they're kind of rounded in shape. We call those G-actin for globulin, globular actin. Much of your protein is made up of this, so there's usually quite a bit of it in your cells. And then here, a couple key points that we're going to need for the rest of today's lecture. So actin can bind to ATP, and it can also hydrolyze it, so split it again into ADP. If actin is bound to ATP, it really likes binding to other actins. So actin ATP will be incorporated into microfilaments because it likes to bind other actins, right? It likes to interact with other actins. Then upon binding, upon becoming part of this microfilament, it hydrolyzes ATP to ADP. And then it doesn't like binding to other actins as much. So you can already tell that this really becomes a very dynamic system. It's not your bones of your body, much more on and off going on. So when it's polymerized, we call it F-actin for filamentous. And here we have a plus end and a minus end. We briefly talked about that too. So these actin monomers are added on both ends if the concentration of them is high enough. With the plus end, the addition is easier. Yes? Yes. Each one binds its own ATP and then becomes incorporated. Yes? Yes. So if you see this little string of beads, each bead is a G-actin. Yes?
Once the G-actin becomes part of the S-actin, does the ADP stay bound to it?
So pretty shortly after it binds after the globular actin becomes part of the filamentous actin, it hydrolyzes the ATP. So it still holds on to the ADP, but this is now a state in which it doesn't like to bind the other actins as well. So it stays bound, but it takes one phosphate group off. Yes?
Can it bind to either end?
Yes, it can bind to either end. It's just that the way that the orientation of these filaments is, we call one having a pointed end and one having a barbed end. The pointed end is pointing towards the minus, and it's less easy for new actins to come in and bind there. So it's less favorable to come in from that side. But given enough G-actins, globular actins, it will happen. So if this is a newly forming actin filament, we can kind of see this actin filament as showing us some history of how it was made. Because we have actin bound to ATP that likes to be added to the filament, and so it makes it grow. But then after it's added, at some point, it hydrolyzes the ATP. So the ones that have been part of this strand longer are much more likely to be bound to ADP than to ATP because they hydrolyze the ATP that was there. So this would then be the plus end, right? Where preferentially new actin ATPs are being added. And even though some, as soon as they're added, might hydrolyze their ATP to ADP and fall off, many more will be added here. So the filament is growing. As they lose or hydrolyze their ATP, they become much more likely to let go of the others, and so to release from this filament. So you can imagine adding here and removing here. It kind of looks like this filament will be walking off the screen, right? Because it shortens on one end and it gets longer on the other end. So actin filaments grow by the addition of actin monomers at either end. really concentration dependent, but it can grow from either end. But it grows faster at the plus end. And this is something, if we remember that, that's going to really help us understand those graphs that are coming out. Each actin monomer has an ATP. It hydrolyzes that to ADP right after it's incorporated. There's a little bit of freedom, I guess, that they have. So here, everybody will have ATP. Then you'll have a little mix of actins that have already lost the phosphate group and actins that are still fully bound to ATP. But then towards this older area, everybody will have ADP. Yes?
How exactly do they stay bound if they're no longer attracted to actin?
It's higher and lower affinity.
Oh.
They will still like each other, but not as much. So it's more easy for them to be lost. And I don't think they just lose from here in the middle. They lose or get added at the ends. And so if nothing else is added, a naked actin filament can disassemble from both ends. We can have proteins that are going to sit on here and cap it and prevent it from disintegrating. Right? So we won't really talk a lot about that, but it will show up in one of the videos that we'll be watching. And then there's one term that I didn't talk about, and that's that term treadmilling here. So treadmilling, the first time I went on a treadmill was terrible. I was one of those people holding onto the bar and my feet were going back. I don't do that very much. I don't do it at all anymore right now. But anyways, the idea is that the treadmill, right, the thing that you walk on, it moves from the start to the end. And that's what's happening in this process, treadmilling. So in treadmilling is the situation where the concentration of those free monomers bound to ATP is such that one end is growing and the other one is getting smaller. So there's net addition to the plus end here and net removal to the minus end. That doesn't mean that there's never any one molecule coming in to bind here, but it's just less likely. So the net effect at this end is loss, and the net effect at this end is a gain. What does that mean? During treadmilling, does the filament grow, shrink, or stay the same? This is a good question, but let's just talk about it instead of trying to do this on our own.
It's the inside, right? In the picture?
I would say stay the same. I would assume that at the same rate as it gets on, it comes out. Well, is this not down to scale? Obviously, it's not that big.
But yeah, as I was saying, I put the cookies in there.
Oh. Okay, after class.
Yeah.
Thank you.
My mom made it. I forgot.
Oh.
I was like, oh, I should probably eat these. But then I saw how much I had, and I was like, I should probably start giving them out.
But then again, this thing, doesn't it start off with one monomer and then it grows?
Is it like that?
Oh, during treadmilling, that's what it's asking.
That's good.
Okay.
So when I said that they're
Okay, that sounds like a challenge.
when I said that there was net growth on one end and net
Oh,
doesn't say anything about how fast the growth was on either end, right? And so treadmilling is the situation where the filament is growing on one end and losing on the other end. But it really only has one particular concentration of two monomers at which it is balanced, where the loss is equal to the gain. So in this instance, with the information that I gave you, we really can't tell.
So let's do.
So that would be answer E.
So if it's different, could you tell?
And we'll get to why that is. Let me see. Did everybody
Like she
change
already
to
told
where they
us
wanted
the
to
rate
be?
of growth or the rate of loss.
Yeah, she said that.
So that's why we can't tell.
But I'm saying if it was, if
Yeah.
she did tell us.
Yeah, then yeah.
Trick question.
Because if it's saying that it grows faster, then it loses faster, then obviously it's going to grow faster.
No, okay. We'll discuss.
We just put on the 2 weeks.
Yeah.
So I'm like, that's how much shit and everybody has on calls. They're calling me. I hope they don't have to call me. Last time they called,
This one doesn't have any sound.
I just want to keep it via email.
So there we have our actin. Is this all in the way? There's some ATP that can be bound to it. And so if it's bound, they probably did yellow in this video. So the actin bound to ATP is yellow. And then when it hydrolyzes the ATP, it becomes blue. So now we can see yellow likes to bind to other actins. And so they can form these spontaneous nuclei that start of a filament. So they bump up to each other and then boom. Now
That's so cute.
they have the start of a filament. And then other actins are going to come in, and after they become incorporated, they hydrolyze their ATP to ADP. Right, and here we see that example where it appears to be walking across the screen. And then there's some accessory proteins that we don't really go into much detail about, but there's profilin and profilin. Profilin prevents or binds ATP bound actin, and it prevents it from forming starting filaments. But you'll see in the next episode that if there is a filament, it makes the elongation go faster. So it prevents nucleation. Doesn't like actin ADP. Here we are. Now we have a little filament bound, and look how fast that's growing. So the profilin promotes the elongation of the actin microfilaments. And then this green guy, cofilin, can come in and break up filaments in the middle, right? Normally the actin monomers are added on one end, but the cofilin actually can help break apart an existing microfilament. And then once you have small filaments, apparently the process accelerates. So these are just some players. Really, I wanted to show you the first part of the video to visualize how Alright, so link is here. You can watch that as many times as you like.
Watch it like 20 times.
Like to.
So we can study this in a test tube. Yes.
So in what situation or why would it be beneficial
it is really good, but that's a good question. So if the cell wants to move somewhere, it needs to change its shape in order to go to this other spot. And so the skeleton is really dynamic to make that happen. For cell movement, let's see, what else? The way, the shape of the plasma membrane. We talked about endocytosis. I can imagine that needs to have some free space, so maybe locally we need to remove the actins, stuff needs to travel. So there's all sorts of dynamic things going on that makes it good to also be able to break down existing filaments. And so in the cell, there's a lot of activity going on, but we like to study things in isolation to better understand it. And so here, we'll talk about a few slides, and I probably will flip back and forth a little bit. Here is an experiment where we're going to be talking about the critical concentration. And this has to do with the multiple choice question that we just went through, because the critical concentration marks the level at which the monomers are in equilibrium with the active filaments. What this means is if you start off with some concentration of monomers and you allow filaments to grow, that means that the concentration of monomers will go down because they get incorporated into the filaments. And at some point, you reach this critical concentration, this moment at which there is an equal amount of addition as there is of removal. And so then the concentration of actin monomers doesn't change anymore. And it turns out that the critical concentration is also the concentration at which the spontaneous nucleation occurs. So filaments are started only at concentration of the monomer that's above the critical concentration. And so if you start off with a little cup with 3 monomers and you allow the system to do its thing, to form the filaments, to elongate them, and at some point reach equilibrium, and you do that for many different concentrations of monomer at the start of your experiment, then you get a graph that can look like this. So on the X, we have the monomer concentration, and on the Y, we have the mass of actin that's incorporated into either monomers or filaments. So if we start here on the very low end of the concentration range, so below the critical concentration, if you let the system sit for a long, long time, despite that there is some actin there, it's below the critical concentration, so we would never get any filaments formed. So whatever actin you add in, it ends up as monomer. So the entire mass of what is in your tube is present as a monomer. If you increase the concentration until you hit that critical concentration, now a tiny little bit of the monomers start to form these nuclei, the start of the microfilament. And then this is going to grow, reduce the concentration of monomer until it is at the critical concentration, and then it won't drop any further because it will be at equilibrium. So if you add in a boatload, tons and tons of actin monomers, and you allow the system to do its thing to fully equilibrate, you get a lot of filaments formed. That's this line here. And you end up with monomers at the critical concentration. Right? So below critical concentration, the monomers stay monomers. At critical concentration, you start to get these nucleation events, but they can't really grow because making these has depleted the monomer concentration, and now there can be no addition because we fall below critical concentration. At the very end, in each of these situations, there will be this balanced treadmilling going on. because we allow the system to come to equilibrium, which means that the actin is at critical concentration. There will be net addition to the plus end and net removal from the minus end, and this will no longer show a net growth, even though there is addition and removal on either end. On the way there, we might see something like this, but this graph deals with a final steady state. And so this picture here would make sense if we were looking at time, which is what we'll do in the next slide. But for now, we're dealing with the steady state at the very end. So if at the steady state, there's balanced treadmilling going on, what if on accident, a couple extra actin monomers are added to the filament, right? This would then drop the concentration to below the critical concentration, which means that growth will stop and you have a little bit of net loss. And now the critical concentration is again reached. So the system keeps itself in balance. And we'll come back to this slide after we go through the next slide, which should make it more clear. Should have not animated this, but left that sit there. So now we're doing one of these experiments. One of the experiments that went into the previous steady state analysis. So now we're looking over time, meaning this is not steady state. Right? We're going to start by adding some amount of actin in the tube, and then we're going to follow over time, x years at a time, what happens to the percent of actin that's incorporated into the filament. So if we start at the very start, all right, so these, at the end here, we'll have a single steady state reached, which you can then plug in as 1 point in the previous graph. But we'll start with, say, 50 micromolar actin subunits. At the very start, nothing is happening. These are just in solution, and they bump into each other, and then at some point, you get that first oligomer form. They're bumping into each other, they're forming a little nucleus to start of a microfilament. What has happened to the concentration that we put in when we reach this point? It goes down, but by a teeny tiny bit, right? We only have a couple of nuclei formed. So a couple of the monomers are now part of a filament. So we still have a lot of free monomers available. And the filaments will be growing on either end, because here at the top you can see we have those critical concentrations. And it turns out that the critical concentration for the plus end and the minus end is different, because at the plus end it's easier to add new monomers, so the addition will go on even if the concentration of free monomers is lower. So the minus end, where it doesn't happen as easily, it takes a higher concentration to start adding free monomers. So this initial bolus of 50 micromolar, most of it is still there, right? We've maybe incorporated 1% of all the actins in a filament. The rest is still freely available. So this oligomer will start growing from either end, because the concentration that's available is above the critical concentration for both the plus end and the minus end. So what's happening here, we are elongating, so we are taking up free monomers out of concentration to put them in these filaments. They can be one or multiple, doesn't really matter in the end. But the concentration of free monomers goes down. So what happens if we reach a concentration of, say, 0.8 micromolar? filament still growing? Alright, let's take a couple minutes and talk to each other. We've depleted the free monomers to the point where we're down to 0.8 micromolar free monomer concentration.
She answered it's still growing, but only on the negative side.
Yeah. And is that the middle picture, right? Is that where the critical concentration is? Where it's like
Right there says concentration of monomers at steady state, so
but that's the above, yeah.
I assume at that point it doesn't really change anymore.
And then the other part where I was like, okay, she lost me. Was, you know how she said if you when she said that where the oligomers or whatever, if you added something, the concentration would end up going higher.
No, where it's in the beginning, as you start making oligomers, you start
Who wants to
losing,
throw
you end up with
something
less.
out there? We've depleted the free monomers to the point that we're now down to 0.8 micromolar. What happens at the plus end, at 0.8 micromolar? Is it growing, stopping, or even decreasing? It's growing. The plus end is still growing because we're above its critical concentration. So at 0.8, what happens at the minus end? It'll stay the same. Are your subunits being added? Yes. But there's no net addition, right? So there's equal amounts of addition as we see loss. No net addition at the minus end. Still net addition at the plus end. So the filament is still growing. Right, so now we're going to go down to 0.1 because we keep growing, we keep adding monomers to our filament, depleting the monomer pool in our test tube.
But if you're at
What would-
0.8, then you just can be at equilibrium.
What would happen next? Would we reach 0.1 micromolar? Well, let's think about it. What would happen at 0.1 micromolar at the minus end?
Before coming out.
That one would start to shrink, right? We're below its critical concentration, so it has a net loss of monomers. And so at 0.1 micromolar, the plus end is stabilizing, right? No net addition. So no net gain or loss. It's not growing on the plus side. It's shrinking on the minus side because that one is now below its critical concentration. So one is stopped, one is shrinking. If it shrinks, what does that do to the concentration of free monomers? It goes back up, right? So somewhere in between 0.1 and 0.8, we're going to find this condition of balanced treadmill. And we can say that we'll put this at 0.45, right in the middle. That's a good guess. But at either end, there's no treadmilling because here, this end is stationary, here, this end is stationary. So in between there, we have treadmilling, and then at one concentration in between there, we have this balanced treadmilling. Yes?
So I know you're saying the plus end, it's easier to add on your plus end. So, okay, so say you're in between the 0.1 to 2 critical concentration.
Yes.
Do they treadmill at the same rate? Like, so does your minus end lose one at the same rate your plus end gains one? Or does they equate just as well?
So that would only be at that critical one concentration of free monomers, where it's exactly equal. But treadmilling can still mean that the filament grows say you're pretty close to the 0.8, maybe 0.7, there's still good growth at the plus end, and the minus end is slowly losing, right? So there's still a net growth in the filament.
So they're kind of independent of each other.
See that it goes through all the things that I want. Ah.
Here's like a point two.
Yes. So
I forget what.
textbooks don't always get it right. Unfortunately, we'll see another example, I think, with muscle contraction. But there's something wrong here with this picture. This depiction of the steady state. I think we kind of talked about it with your question. I forget your name, the yellow sweater. What's wrong with, I'm not asking you, what's wrong with this picture?
Plus, you should have a net, net in.
Does the steady state ever look like that?
So on the plus end, you should have like
Why
a
not?
net of increase, but on the point A, you should have a
Decrease?
mesh equilibrium.
Okay.
Assuming that's at point A, because it doesn't say.
So this picture here is suggesting that there's addition and removal at the minus end, and addition and equal removal at the plus end. So what does that suggest for the critical concentration for both ends? That they're equal, right? And they're not. So there's never a situation where there's equal addition and removal on both ends. There's not a single actin monomer concentration that you can find that would do that. So we really need to remove some things from here. So at the equilibrium phase, because it's easier to add to the plus end, we can keep this, chuck this, and at the minus end it's easier to remove than to add, so we can keep this and chuck this. I think that's my next animation, yes. So now it looks much better. So a brief run through, we start up with all our actins as free monomers. Some of them find each other, love each other, and make a filament, and the filament then starts growing. And the growth occurs on both ends. Net growth occurs on both ends. There's still actin ADPs that are falling off, right? They've been incorporated for a while, they've hydrolyzed their ATP, so they have ADP bound, they will fall off, but the growth is bigger because we're above critical concentration. So as long as that is true, both ends of the filaments are growing, then we'll reach the critical concentration of the minus end. That one will stop growing, whereas the plus end is still growing, so we still have a growth of the filament. But as soon as you drop below the critical concentration of the minus end, that one starts net losing monomers, whereas the plus end is still net gaining monomers. And then this means that we're still incorporating monomers, we're still decreasing the free concentration of the subunits, but we'll never reach the critical concentration of the plus end, because at that point both ends will start to lose and it will shrink, increasing the concentration of free monomers, which will allow for growth. So in our test tube, it always ends up with this balanced situation that is determined by the critical concentration. So we started off with all our actin subunits as monomers. We've incorporated a whole bunch, but this critical concentration amount is always going to stay as free monomers. There'll never be all of them incorporated. So let's think about this. The experiment we just talked through started with 50 micromolar of free monomers. What would this curve look like if we started it at 10 micromolars? Talk to your neighbors, think about it with yourself, and then I'll ask two people to come up and draw it on the board so that we have something to talk about. That's easier than me pointing a light.
To your right. So there's no one there, so.
That sucks. You're still stuck with me.
What would the curve look like if you started with 10 micromolar?
Do you need paper or can we just like draw it out?
Just draw it on this.
On here?
On here. No kidding. So one of them's at 0.8, the other one's 0.1. I hated stats. Yeah, stats exam? No. Are you ready for it?
It's on here. I'm pretty sure it's like
So, can you, well, you're gonna draw on that? Okay, so this is starting at 50. So that means 0 would be 10, 100 would be 0, right? So then you start with 10, and then when we get to like, let's say 0.1, we just find like way up here.
are we still going off
Yeah.
oh, this step I don't think
And then that's when we only add, so that's when we go into
Yeah, do I have
equilibrium
a 1 minute?
for
Brave
the
balls is
top
here.
one.
Okay.
But the bottom is going to start losing everything.
because it's long concentration.
Yeah, the higher you get, the less
Yeah, I guess.
pretty subunits. And that's why this line is the concentration line that's in place. Like you cannot go higher. Because then you get to 0.1.
Yeah. Okay, yeah, but I guess still 10 is still above it.
So would it make it more negative or would it be strong?
Would it make it one more negative? What do you mean by more negative?
Like, would there be, actually, I mean,
Like,
would there be less than negative?
once it gets up here, it's going to start to go back down because as this side starts to decrease, it starts to go back down.
Forward and enlighten